Hey everyone, this is NIRANJANA and we'll be discussing the biomedical applications of the Fourier transform. Let's start with the video. First, let's start with a callback to the Fourier series as we discussed in class. As we know, the Fourier series is nothing but a very easy way by which we can decompose a periodic complicated function into an infinite sum of sines and cosines. The coefficients for the sines and the cosines can be found out using the equation that's given on screen. This is sometimes very useful because a function may be difficult to analyze in the time domain and the Fourier series may lead us to answers. Let's watch a video and see how the sines and cosines can make up a square wave. As you can see, initially it just looks like a sine wave and we cannot see the square wave. But as more and more harmonics are added, it quickly starts approximating a square waveform. Let's move on to the Fourier transform. While the Fourier series provides us answers for periodic functions, the Fourier transform is a vastly more useful generalization by which we can get the frequency components of non-periodic waveforms as well. It's very useful and lets us break up complicated functions into its frequency components and can give us the frequency response of a function as well. However, the Fourier transform cannot be applied to sample data, and for the sake of this video, we'll have to resort to the discrete Fourier transform. The discrete Fourier transform helps us to identify the frequency components in discrete signals or sample signals that we get back from the machines. Throughout the video, we'll be applying the discrete Fourier transform on signals. The fast Fourier transform is an algorithm that can give us the discrete Fourier transform rather efficiently. It's fast, and for the sake of this video, we'll not be looking at the mathematical intricacies, but rather using Python libraries. First, we'll see how we can apply these in the field of denoising signals. Let's try applying it to a few biomedical signals and see. Let's look at what the steps to denoise a function using the Fourier transform are. First, you have the recorded noisy signal. Now you take the Fourier transform of the signal that you have and then you identify the noisy components from the frequency response. Now that you have the Fourier transform, you can identify which frequency components is causing the unwanted noise and set those coefficients to 0 by applying a filter, such as a low pass, high pass, or a band pass filter. Then you can apply the inverse Fourier transform and obtain the clean signal back. Let's try applying this to a couple of signals. First up, we have the ECG signal. Let's look at a simulation for this. Here, I have a clean ECG signal that doesn't have any noise added. This is set to a heartbeat of 80 beats per minute, which gives it a frequency of about 1.3 Hz. Let's look at the Fourier transform. As you expect, we'll zoom in here. Here you can see that there's not noise at all and you just have the main useful information at 1.3 Hz. Let's try adding some noise into the signal. Here I've introduced some noise. Let's try. Here we get the noisy ECG signal, which looks very different from the actual ECG. In real life, this noise could be due to machine feedback or environmental factors, and it makes it difficult to analyze if a person has any heart issue. Let's look at the Fourier transform of this. As you can see, there's a lot more noise here and the components here are completely unwanted. Let's try to apply a bandpass filter and remove these components. Let's keep a low cutoff frequency of about 0.75 Hz and let's keep the high cutoff as 15 and see what we get. As you can see, this is very close to the original function, but there's a little too much noise. Let's try reducing the high cutoff. This is a very close approximation of the original signal that we have here, but it's not quite there. We can improve on this using other transforms such as the wavelet transform, which we'll discuss later in the video. Similar to the ECG signal, we also have the PPG signal, which here, as you can see, has a lot of unwanted noise. In real life, this noise could be because of environmental factors, or it could be because of the mains power lines, which is a very common issue. Here we can identify that this is the component that we need and the rest of it is just noise. And we can put it through a filter once we've identified the cutoff frequencies. This is a very simple form of a filter with a built-in amplifier. This would amplify the actual frequencies that we need while cutting off these low frequencies and unwanted high mains frequencies. This involves using resistors, capacitors, and op-amps. Let's move on to other uses of the Fourier transform. Let's look at a couple of examples involving MRI image reconstruction from the Fourier transform. First, let's familiarize ourselves with the 2D Fourier transform. The 2D Fourier transform is nothing but the Fourier transform applied to images, which are two-dimensional because of their length and width. It will convert the image from the spatial domain to the frequency domain and tell us how much of each frequency is present in an image. We have the low frequencies in the center of the image, whereas the higher frequencies, which represents details and edges, will be in the sides. Let's look at a few examples of the Fourier transform of an image. This one is very easy to analyze. If we look here and consider this as the y direction and this is the x direction, we see that in the y direction there is no change at all. It's very constant. However, if you look in the x direction, you see this sort of alternating pattern, which in reality is nothing but a sine wave with a constant frequency. And because this is a sine wave, the Fourier transform will give us only one frequency, which will be the frequency of this. And that's exactly what we have in the Fourier transform of this image. Similarly, this will also have 2 points with a bit of shading because of its shape. And that is what we see here. The MRI reconstruction involves much more difficult image processing. Let's look at how the MRI works. So the MRI machine contains powerful magnets that create strong magnetic fields and tries to align the protons in the person's body along with the direction. This causes the protons to agitate and go to higher energy levels. Once the protons in the hydrogen atoms come down, they will release signals that will be captured by the MRI and collected as raw data in the form of K-space. The K-space is not data that can be interpreted. We'll need to convert it back to the actual image. Thankfully, the Fourier transform comes in very handy here, as the Fourier transform of the K-space data will give us the actual data that we need to interpret. So first, you have a person who's lying in the MRI machine, and through data sampling, we'll have the K-space data. Once we have filtered the data, we can reconstruct it back by the use of a simple Fourier transform. This shows just how powerful the 2D Fourier transform actually is. Here we can see that the limitation of the K-space is that because it's not infinite, some information will be lost or blurred. Here we can see because of how sharp it is, the image is also not blurred. However, here, this blurring causes a lack of resolution in the image. The lack of resolution can be rectified by running the signal received through a Gaussian filter. Here we can see as it gets smoother and smoother, the image also becomes of higher quality. So far, we have discussed just how useful the Fourier transform is in the biomedical field. However, the Fourier transform also has some dangerous pitfalls. For example, these two graphs are completely different in the time domain except for the fact that their component frequencies are the same, 1 Hz and 3 Hz. However, in the Fourier transform, this would be completely indistinguishable because both of them would have 2 peaks at 1 Hz and 3 Hz respectively. And this causes a loss of information. This brings in the need for wavelet transforms. We will not be discussing them in much depth, but we will be discussing why they are more useful than Fourier transforms in denoising and other factors. The wavelet transforms offer a good compromise for us between the time and the frequency information, whereas the Fourier transforms just offer 0 time domain information. And since wavelets come in multiple shapes, it provides much more versatility, and you can adjust it to the shape of the signal that we need. Biomedical signals like the ECG and PPG are quasi-periodic, which means that they have periodicity, however, the time period changes continuously throughout the duration. The Fourier transform cannot analyze this very well. And the wavelet transform provides a much more powerful tool for things like the ECG and PPG denoising. So, let's quickly recap everything that we saw in the video. First, we understood what the Fourier transform was and why we could not apply the continuous Fourier transform to the discrete signals. Then we learned the advantage of the discrete Fourier transforms and the fast Fourier transforms. We also saw a couple of simulations where we used the Fourier transform to remove noise from scans. We saw how the Fourier transform in the 2 dimensions helped us to reconstruct the image from MRIs and provided us with the useful images. Then we looked at the shortcomings of the Fourier transform, where it could not give us any time domain information or deal with quasi-periodic signals. I hope that this video was useful. Thank you for watching.